Hello, this is Mr. White, and this video is on optimization, part 1. Optimization is often called applied minimum and maximum problems, and our textbook does include these general guidelines, which I'll roughly adhere to, so I suggest you have them by your side as we go through this. Here are the two exercises we will cover today. Let's get that out of the way and begin. We are seeking two positive numbers such that the second is the square of the reciprocal of the first and the sum is a minimum. So for example, if I just chose one positive number at random and say the number 4, the second number needs to be the square of its reciprocal. So 1 over 4 squared. And in this case, this would be 4 and 1/16. So our goal is to try to make this resulting sum as small as possible. All right, let's bring up the guidelines here. And I'm going to admit that step number 1, there's not a whole lot to do in this particular problem for step 1. About all you could do is acknowledge that you're going to call these positive numbers x and y, although I wouldn't completely blame you if you left off explicitly writing that step out. So let's get to step number 2. We're going to write a primary equation for the quantity that is to be maximized or minimized. In this case, we are looking for a minimum, not a maximum. We're looking for a minimum. And what is it we're trying to minimize? Well, we're trying to minimize the sum, right? So our primary equation is going to be for the thing we are trying to minimize, the sum. And let's call that S. And I guess I should be clear and say that's the sum S. And that's going to equal x plus y. That's the definition of a sum last time I checked. So notice that S is currently written in terms of two separate variables. So when I bring up step number 3 here, reduce the primary equation to one having a single independent variable, we want to get these two variables down to just one. Whether it be x or y, we don't really care, but we need just one or the other. And that may involve the use of a secondary equation, which relates the two current variables that we have here. So what is this relation? How are we going to get an equation that relates x and y? Well, that's what this piece of information is. The second is the square of the reciprocal of the first. Okay, so for step number 3, our secondary equation is going to say that the second number is the square of the reciprocal of the first. Although I find it easier to just put 1 over x squared. They are the same thing after all. So one more time, primary equation is the thing that you want to make as big or small as possible. And secondary equation is the relationship that's going to relate these two variables and allow us to write the primary equation in terms of one variable. So let's go ahead and do that. Let's combine those two equations and say that S equals x plus, and what I'm going to write instead of y? Well, I'm going to write 1 over x squared because that is what y equals. And now I have completed step number 3 because I have that primary equation written in terms of just one variable x. Okay, step number 4. Determine the feasible domain of the primary equation. Well, in this case, we're told that these had to be positive numbers. So about all we can write for step number 4 is to say, well, what values are we allowing for x over here? We're only allowing positive values. That's another step where honestly I could forgive you if you don't explicitly write that step down. However, if you gave a negative value of x for your final answer, then you would be penalized, of course. So step number 5 is where we start to feel on some familiar territory. We're asked to find the minimum or maximum, find the extrema of this function s here. And even though it says using the first or second derivative test, I'm going to admit that we tend to allow certain shortcuts there, as you'll see here in just a moment. Since that's the last step mentioned in this process, I'll go ahead and get rid of these guidelines and just clear up some board space. So step number 5, whether I'm thinking first or second derivative test, they both start with taking critical numbers. They both start with deriving s. And if I think of s, if I write it in a little more user-friendly way, x plus x to the -2, then it makes deriving a little easier, and I get the derivative of s is equal to 1, derivative of x, right, minus 2x to the -3. That's the derivative of our second term. And that's what we set equal to 0 or undefined. This second term, minus 2x to the -3, is the same as minus 2 over x cubed. And if I write the first term with a common denominator, x cubed over x cubed, and set it to 0, and then I write them, and then I implement the common denominator. There, hope you didn't blink. I notice that the only thing that is going to make this derivative undefined is when x is equal to 0. But remember we said that x has to be a positive number, it can't equal to 0. So we know we're not going to get this undefined case. Now what about when the numerator equals 0? Well, that's going to yield x equals 2 to the 1/3 power, or cube root of 2 if you prefer. Either way, that amounts to about 1.2599, 1.260. Now remember, we said y is equal to the reciprocal squared of x, right? So if I type that in the calculator, let's just move this over, I would get y equals, or I guess before I type it in the calculator, 1 over the x value that I just found squared. About 0.630 squared. Or not squared, just 0.630. Interesting coincidence, or is it not a coincidence, that that one number is twice the other one? Strange. Anyway, you know what? I'm going to put a box around that. And this is where I'm taking a bit of a shortcut. I officially haven't completed the first or the second derivative test, but using a little bit of logic, I can conclude that these are a minimum value. These represent a minimum sum, not a maximum sum. One way I may argue that is to say that, okay, well, this is the only critical number, so let me just pick some other value of x like we did earlier. Remember when we took 4 and we added 1 over 4 squared, and we got 4 and 1/16? Well, that's clearly bigger than the sum of these two numbers. This sum here is bigger than the sum of the two we just calculated a moment ago. So clearly, these two numbers, the 1.260 and the 0.630, must represent a minimum sum, not a maximum sum. This is a rare time in calculus where I'd say you can use that kind of logic. Normally, we're a little more stringent about completing the first or second derivative test. I'll also point out that if I use the calculator, and I calculate the value of x that you see here, and then I add x plus the square of its reciprocal, I see that this is the sum that I get. Whereas if I were to take a number that was slightly smaller than x, like 1.2 exactly, and if I were to type that, I see that I'm getting 1.89 something, which is bigger than the sum of our optimal numbers. If I typed in a number a little bit bigger than 1.256, if I typed in 1.3, I see that again, I'm getting a number that's a little bit bigger. This is clearly our optimum sum over here. All right, let's get on to the next exercise. Okay, so here's a picture of a 60-quart stock pot that I found off the internet. And we want to know what dimensions would minimize the outer surface area, neglecting the handles. So what is it we're trying to make as small as possible? Well, the area, the surface area of this outside surface. And we will count the bottom there, underneath the pot. We'll count that as part of the outer surface area as well. What we will not count is the inside of the pot, or the handles themselves too, right? So the outer surface area is what we're trying to. And not only do we want to know the dimensions of the pot, not only are we asking for the dimensions of the pot, the radius and the height presumably, but we also want to know what is the outer surface area that optimal radius and height will produce. So before we get knee deep in the optimization process, let's just try to get our heads around what we're wrestling with here. Of course, we're going to conceptualize this pot as a cylinder, a right circular cylinder to be exact. And as I switch over to GeoGebra here, we'll get a sense here that how radius and height are competing with each other here. One thing I just realized I forgot to mention is that since quarts are not a very friendly unit of measure for us to deal with here in calculus, we're going to go ahead and use the conversion factor, that 1 quart is about 57.75 cubic inches. So for this 60 quart pot here, that means that the volume is actually going to turn out to be 3,465 cubic inches according to that conversion factor. So you'll see on the GeoGebra file that I've already got this constructed to where the volume is set to 3465 and the radius is on a slider. And right now the radius is 5 inches and the height is 44.118 inches. I'm dealing exclusively with inches here in this construction. And as you might expect, for that really tall pot, we can expect that we'd get a lot of surface area there. That 44-inch height is going to make our surface area quite large. But as I bring the height down, the radius gets bigger. So here's the height decreasing, but in order to compensate for that and keep the 3465 volume that we wanted, the radius has to get bigger. So height gets smaller, radius gets bigger. And we're getting to something that looks a little bit more reasonable as far as a pot goes. But obviously I could keep on going to the other extreme here as well. And as I make the radius bigger and bigger and bigger, it's still keeping that 3465 volume. But as I make the radius bigger and bigger and bigger, we see that that bottom surface is now going to make for a really large surface area as well. The bottom of the pot is going to create a surface area that is certainly not optimal. Okay, so we get the sense that radius and height are competing against each other, and this extreme is not good. This extreme is not good, but that there's somewhere, some sweet spot in the middle where we've got the optimal surface. Just one last thing too. If I were to graph surface area as a function of radius, that's what I've got on the right-hand side of the screen. So even though it's not labeled, the horizontal axis represents radius, the vertical axis represents surface area. So right now my radius is set to 4.5. And we can tell from the graph on the right that the surface area is somewhere above 1,500 square inches. And again, as I make the radius bigger and the height smaller, we see that the surface area is going down as we predicted. It's going down lower and lower. The surface area is down to about 1,000 it looks like. But then again, we've just passed the sweet spot. Now as the radius grows, the surface area is back to getting bigger. So where do we want to be? We want to be right at that sweet spot, which appears to be somewhere around a radius of 10 and would give us a total surface area somewhere around 1,000. So that's what we're trying to find. I wanted to show that conceptually, but now let's stop cheating, let's stop using GeoGebra, and let's try to come up with a similar answer using calculus. So again, I'm going to get rid of the photograph of the pot. We'll just consider the cylindrical sketch that you see there. And speaking of sketches, that is part of step 1 in this process. We're to identify all given quantities and quantities to be determined, and when feasible, make a sketch. So I would consider this sketch, and let's go ahead and label height and radius there. Let's go ahead and consider that, as well as this piece of information, part of our step number 1. Now, step number 2 is where I could imagine that a lot of students might have a little bit of difficulty. This is where we write the primary equation for the quantity that is to be maximized, but in this case, minimized, right? That's the surface area. So step number 2 is where we write an equation for the thing we want to make as small as possible, the surface area. And I'm going to make this a little bit smaller here. And let's recall from geometry class how you approach surface area. Remember how you essentially said that you could slit this cylinder down the side and then unwrap the side? So I'll try to just continue this sketch here. Imagine that that's the paper label of a can. And so here I'm removing the label of the can, and now I'm going to unwrap that label into the rectangular piece of paper that it is. So if I unwrap it into a rectangle, and then we correlate those 3 sketches, again, we're trying to calculate the surface area of the side for right now, and we'll take a look at the bottom in a moment. But notice that the height of the can is the same as the height of the label, even when it's unwrapped. So we can go ahead and label that H. Now, as far as the length of this rectangle, whose area we're about to compute, isn't that equivalent to this wraparound here and this total circumference of the pot? Or the can, depending on what analogy I'm using? Well, recall that the formula for circumference of a circle is going to be 2 pi r. So that is exactly what we will label this rectangle. And again, that 2 pi r represents this total distance around the pot. So this is a rectangle representing the side surface area. And if we want to ask ourselves what's the area of that rectangle, it's going to be length times width, or base times height. 2 pi r times h. Shrink that down a little bit, and we'll put in for surface area 2 pi r times h. Now we need to add the bottom of the pot, right? So we did say we wouldn't count the top there because it's an open top pot, but we do need to count that bottom surface under there of the pot. That's part of the surface area that we want. So what's that area going to be? Well, it's circular in shape, so its area is going to be pi r squared. And that is our surface area for the side of the pot, the outer side of the pot, and the bottom of the pot. Okay, let me clear some of these sketches out of here. Let's get those out of here. And let's take a look at step number 3. Notice that in step number 2, again, we wrote our primary equation, but notice that it's got 2 independent variables. It's got r and h. So step number 3 is where we get this down to 1 independent variable. And we say independent, we notice that they really kind of do depend on each other, as we'll see here. So step 3 is where we reduce the primary equation to one having a single independent variable, whether we get it down to just r's or whether we get it down to completely in terms of h, doesn't really matter. We'll go with whatever's easiest. And this may involve the use of secondary equations that relate the independent variables. So if there's a secondary equation that can relate r and h, that will allow us to get this surface area in terms of a single variable. So what else is going to relate r and h? Well, how about volume, right? So let's ask ourselves, what's the volume of a right circular cylinder? And that's going to be pi r squared, the area of the circular base, times the height of the cylinder. And in this case, we already said earlier that the volume is something that we know, that is fixed. We're dealing exclusively with inches here, so to the chagrin of other math teachers, I'm sure I'm going to not write the units here, but I will include them in my final answer, I promise. So there are our primary and secondary equations. Feeling a little cramped here, so let's move this down. And again, the idea is that I can take this equation and combine it with this one and get surface area in terms of a single independent variable. So let's do that. Now, do I want to get this completely in terms of r or in terms of h? Let's do what's ever easiest. And I think the easiest thing to do would be to write this, to solve this for h, and then substitute in for that h right there. And let's get this equation in completely in terms of r. So if I rearrange this one on the left for h, I'm going to get h equals 3465 divided by pi r squared. And then when I plug that h value in over here, it will give me surface area equals 2 pi r times this expression for h, written in terms of r, over pi r squared, plus pi r squared. And something great happens here. The pi's cancel out or divide each other out, and this r divides out one of the r's down on the bottom. So this simplifies to surface area equals, it's going to be 2 times 3465 over r. So 6930 over r plus pi r squared. And in anticipation of the calculus step next, let's write that 6930 over r. Let's write it as 6930 times r to the negative 1. Now we've completed step 3. We've reduced this primary equation down to an equation that is just a single independent variable, r. Let's scroll down a bit. As far as step number 4 goes, determining the feasible domain of the equation, we ask ourselves, what are the reasonable values of r over here? Well, we know that we're dealing with a real-world physical pot, so we can't let r be negative or equal to 0, right? There's step 4. And finally, step number 5 is where we use our familiar calculus techniques to find the extreme. In this case, we're expecting a minimum, right? And we'll use either something akin to the first or second derivative test, although as you'll see, I am allowable, or I am agreeable to certain shortcuts. So let's get to step 5. Since that's our last step, I'll get these guidelines out of here. And I'm going to do step number 5 rather quickly because this is rather familiar ground here. We know we start by taking the derivative and finding critical numbers. So let's take the derivative of the surface area and get surface area prime equals, if I derive this term, I get negative 6930 r to the negative 2. And if I derive this term, I'm going to get plus 2 pi r. And since I'm seeking critical numbers, we set that equal to 0 or undefined. Now it's just algebra. This is going to be negative 6930 over r squared. And if we want to do common denominators, we'll do plus 2 pi r times r squared, gives us r cubed, over r squared. So again, I'm just going for common denominators here, equals 0. I'll go ahead and write or undefined, but let's take a look at that real quickly. Notice the only thing that's going to make this undefined is when r is equal to 0. And we already said back in the feasible domain, and just using our common sense, the radius can't equal 0 for this pot. So let's go ahead and say that, okay, whatever critical number may give us undefined really isn't going to work out. So let's see what's going to make this equal to 0. Why don't we go ahead and multiply both sides by r squared here. And that will give me just negative 6930 plus 2 pi r cubed equals 0. And if I rearrange that, I can get r cubed equals 3465 over pi. Of course, pause if you need a moment to catch up. We'll raise both sides to the 1/3 power to get r by itself. And that will give us r equal 10.332. since that's an approximation that I've used a calculator to get, I'll put approximately equal, and since I'm nearing my final answer, I'll go ahead and put the units in as I promised I would. And again, this is where I'm probably more permissive than other calculus teachers may be. Do we really have to finish the whole first and second derivative test and prove that this is a minimum? Well, I'd say that our earlier logic would make us comfortable in concluding that this is a minimum. So let's go ahead and find what the remaining things we need to know are. We need to find the other dimension, we need to find the height, and we also were asked what is the actual minimum surface area we get. Well, I'm just going to say real quickly that what we're going to do to find that out is we're going to use this equation right here. If I plug that value of r we got into that equation, and then if I take that r and that h value and plug it into this equation, or I could just plug r into this one, right? That's going to give me my surface area. So let's do that real quickly. Now, something interesting worth noting is that when you're calculating h, notice that when you plug 10.332 into the formula for h, notice that you get 10.332 as an output. That seems like an odd coincidence that it turned out that our optimal radius here and our optimal height both turned out to be the same number. Kind of strange, isn't it? The surface area turned out to be 1006.097 inch squared. I'm just using the AP convention of 3 decimal places. And that, ladies and gentlemen, is our optimal answer. I'll remind you that it was consistent with what we were anticipating back when we were looking at GeoGebra.